Hello everyone. Today we have a quite tricky problem at hand. So, p of x is a polynomial with integer coefficients. If p of 14 times p of 41 is odd, prove that there are no integer solutions to p of x is equal to 0. How the fuck do we do this? Well, actually, it isn't that hard. Let us only think about the last statement and the first one. Okay, so if p of 14 times p of 41 is odd, and it only has integer coefficients, meaning that both are integers, what does that mean? That means that both of them are odd, right? Because anything times an even number is even. So therefore, we know that both p of 14 and p of 41 is odd. And now, okay, so how do we prove that it has no integer solutions? Or integer roots, you could say. Well, if we could prove that it's always odd, then that would be really nice, because 0 is an odd even number, even number. So therefore, we would basically be done, because then it could never be 0. It could only be odd numbers. And that's the way we're gonna go about it. So if we know that both p of 14 and p of 41 are odd, how do we prove that p is odd for all integers? Well, here we have an even and an odd number. So if we can just prove that p of x plus an 2 times any integer k in modulus 2 is just p of x, then we would be done, right? Because if we know, yes, because if we're just adding or subtracting any multiple of 2, then if we just know that it works for both even and odd, then we can reach any integer with this, and therefore refer back to 14 and 41. So how do we show this? And why is this obvious? Well, if I'm just gonna argue first, okay? So if p of x only has real coefficients, and we're just adding a 2 times k here, and the definition of a polynomial is that the exponents are always integers also, when we then use the modulus 2, all the terms that that this part will have affected will just basically disappear, right? So if I just write out, let's say that, yeah, we can have that p of x is equal to
some integer a1 times x to the power of n1 plus a2 times x to the power of n2 plus and so on down to, I don't know, the grade of this polynomial. We'll call it, the grade is grade g. Should we just n, but nah, it doesn't matter. All the way down to a g of, no, sorry, we can just do this. I'm sorry. This shouldn't be a g here.
It should just be grade n, exactly how I wanted it.
So grade n, and then just n minus 1, of course. I don't know what the fuck I'm doing. N minus 1 all the way down to a g of x to the power of 0. Sorry, a n.
Fuck. Yes. And then plus some constant c. Here, if we were to plug in x plus 2k in here, since this is an integer and n is an integer, what do we know will happen? Well, if we have some kind of, okay, I can just write it up, x plus 2k to the power of n, what will this be? Well, this will be n to the power of, x to the power of n plus 2k times n times x to the power of n minus 1, and plus a bunch of terms, all of them including, and then just plus a bunch of terms all the way down to 2k to the power of n. And as we can see, all of these terms contain a 2. So therefore, when we do modulus 2 with this, we just get x to the power of n left. And now if we put a factor in front here, still doesn't matter. I can do that here. We get a1, then we get an a1 here, and we get a1 in front of that, and then we get an a1 in front of that. It just multiplies everywhere, and it doesn't change anything at all. So this is basically the proof. We just show that for any integer coefficient and exponent, this statement holds. And if this is true, then we know that, okay, any even number can then, with the utilization of a nice k, can then be referred back to 14, and any odd number can then be referred back to 41, and both of those are odd. So therefore, every possible integer input into P gives us an odd value in return. So therefore, every integer yields an odd value, and therefore it can never yield, nothing yields 0. No integer yields 0, because every integer yields an odd number, and 0 is not odd. So that was everything. Proof concluded, and I hope you enjoyed the video. Have a good one. Bye-bye.